Okay, so in this video I'm going to talk about transfer of momentum, heat, and species, and we will see that they are analogous. So I already explained what momentum is, that it's just movement, so energy in the form of movement. Heat is as well energy, but in form of heat, and species is something else that is not related with energy itself. If we see it in the viewpoint of chemistry, let's say, because these videos are intended to be a guide for chemical engineers or students of chemical engineering. So basically, if we have a fluid, because this is fluid mechanics what we are studying here, let's say we have two plates. What can I use here? What color? Let's use just this one. Let's use this. This is going to be one plate, second plate, okay? And here in the middle we have, okay, not that. Here in the middle, let's say here. Here in the middle we have just some fluid going, or just in rest, okay? Let's say it's in rest. So it's not moving, but it's just at rest. Then we decided to push or pull, in this case, let's say we pull this plate, the upper plate, with a force F. Okay? So if we do so, and this plate, the lower plate, is going to be static, we will see that the fluid, so let's say we're not talking about this in steady state yet, but let's say we start seeing something like the fluid here starts to move, right? Starts to move while the fluid at the bottom is still static. Okay, so we start seeing something like that. Let's say here what I had, let me change this a little bit. What I had here at the beginning was actually something like this column of all of them are aligned each other. Okay, let's say they all are up to this point. Okay, so those are just lines coming to the same point, just my reference for explaining what's going on here. So what we can see is that this starts to move, of course, to the right, because I'm pulling the upper plate with a force F. So, and that's what's happening here, transport of momentum, because it's going to be from fluid layer to fluid layer. So the molecules in the upper layer are going to transfer momentum to the molecules in lower layers. And after we do some analysis of this, so I'm not going to analyze this in much detail, but we, or the physicists already, the engineers, realize that this force that we are applying here is going to be proportional to the area times the velocity, okay, over this distance. What is the distance? It's just distance between the two plates. Okay, and the velocity, of course, the velocity here at the top is going to be the velocity of the plate, but the velocity is going to change, right? So the velocity here is not going to be the same velocity here. It's going to be, let's say, diminished till the point here that the velocity at the very down plate, or the down layer, it's going to be 0. That's what we call the no slipper condition. So when we convert this proportionality into a equation, let's change this a little bit more. we can realize that we get a coefficient here. Let's put a negative here, minus a, if we do differential, so that means from layer to layer we want to define a profile. As I already told you, there are differential balances, so we are going to see, so if we put our reference here like y and x, right, so of course it's going to change here, and we can see that the transfer of force or momentum is going to be from upper to lower level. That's why it is negative. So, and this velocity is going to be just the velocity in every point here. So if we integrate, we're going to have the average velocity, let's say, or we could actually get a profile here, you know, like a u in function of y, something like this, you know. But yeah, okay, it depends on, I mean, the function we're going to get, but it could be parabolic, it could be yeah, linear or whatever. And this mu here is what we call dynamic viscosity in the previous video. That is just the resistance to flow under an external force, we said. If we didn't have this force here, instead just gravity, this would be some kinematic viscosity, but this is not the case. So if we divide both sides by, remember this is a vector, right? We divide both sides by the area, we're going to get force over area. But this is not, we can say this is pressure, right? This is not pressure because this is a tangential force, and this is what we call shear stress. So shear stress is going to be defined by two sub-indices, y and x. Why this way? Because the second, I always remember this way, the second one is going to be the direction of the vector. So in this case it's in the x direction. And then we can tell that the shear stress is going to be equal to the change in the velocity over this distance, let's say, over this horizon, can I tell, times the negative of the dynamic viscosity, or just the viscosity, right? Of course, if we multiply by area, we're going to get, this is a vector too, okay? Of course, if we multiply by area, we're going to get just like force is going to be equal to shear stress times area, okay? So keep this in mind. And for heat, it's going to be very similar. Just think about a material. Let's say this is not, we can think about liquids as well. So let's say you don't have this force anymore, but you simply have the liquid here, and you put a heater here. So you're heating up this surface, okay? You start heating up, so temperature goes up here. So the temperature here is very standard sample, 100 Celsius, and here is going to be 20 Celsius. Of course, after a couple of minutes, sorry, the temperature here is not going to be 20 anymore, right? It's going to be, I don't know, maybe 30, right? And after some time in the future, this temperature is not going to be 30 anymore, but maybe 50, and so on, till we reach an equilibrium in which the temperature in the entire thing is going to be, yeah, well distributed, you know, like it depends, but we will get as well a profile here, and we can actually, so this is what we had here. This is what we call Newton's law, okay? And there is a law as well for temperature. So we can realize as well, if we think about not the movement but about temperature, we will get something similar to this as well, some profile like this, okay? So this law is going to be called Fourier's law, and it's very similar. So basically Q, which is the heat, is going to be equal to negative of the thermal conductivity, which is a constant as well, times the area times the change in temperature over the distance. As you can see, they are analogous, right? And then if we divide by the area, we're going to get the small q, which is per unit area. It's going to be equal to temperature over dy. And why these two are negative? Again, I'm telling you because we are going from high level of energy to lower level of energy, so a vector is going to be moving. Let's say the energy is going to be moving from upper to lower levels of energy. As well, in the previous video we talked about the Prandtl number, I believe, or I'm not totally sure about it, but Prandtl, it's going to tell us just so we have a relation between the kinematic viscosity, okay, which is kappa, over the kinematic viscosity, which is actually something like this, over kappa, which is actually thermal diffusivity. Okay, so kinematic viscosity, let's remember that's the viscosity over density, and this one here is going to be just the thermal diffusivity over the rho over Cp. Okay, and this is a way to measure how much, so it's just a ratio of momentum and heat transferred in a fluid. So just to know how good it's the heat transferred and how is that related with the momentum transferred in the fluid. So the units of this is meter squared over second at the bottom as well. That's why this is a dimensionless number, which is very important, Prandtl number. Yeah, so I think that's all I wanted to show you in this video, and there is as well some very similar law. So we said this is Newton's law, this is Fick's law, and this is Fourier's law, and there is another law for species, transfer of a species, which is called Fick's law. Okay, and this Fick's law is something you can look up in Google or something like that, but it's going to have very similar form, which is simply like a composition. It's going to be proportional to the change in some unit, in some let's say concentration over the change in y, and of course this is not the concentration. So it's basically, let me just clarify that very quickly, because I don't want to lift anything just on the air. So at the end we will get Fick's law. It's going to be the diffusion flux is going to be equal to the the diffusivity times the change in the concentration over dy. As you can see, they all have the same form. Okay, so yeah, and that's all I want to explain in this video.